Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back, everyone. Today we're diving into something truly immense, maybe the biggest, emptiest structures we know of. The cosmic voids. These are just these enormous gaps you see in the large-scale structure of the universe, the places where gravity seems weakest, and almost everything seems to have, well, cleared out. For a long time, people pretty much assumed they were just completely empty. Huge black nothings, like holes punched in space. But now we actually have the tools, the technology to map these things out, see how they evolve. So our goal today is to really dig into the latest findings and figure out what's actually in there, if anything. We've pulled together the research to give you the clearest possible picture of what these unbelievably vast spaces contain, because the answer isn't just nothing. It's more interesting than that. The scale, though, it's almost impossible to really get your head around. We'll try.
Yeah, that nothing at all idea is the starting point, absolutely. And it's true, they are mostly defined by what's not there, a profound lack of matter. But the key thing, the really crucial insight from the material we looked at, is that they aren't totally 100% empty. Not across their entire colossal volume anyway. They're definitely the closest thing to a vacuum we have, sure, but there's still structure. There's a great analogy that helps, I think. Imagine deserts on Earth.
Okay.
Like, say, the empty quarter in Arabia. It's defined by a lack of water, a lack of big life forms. You wouldn't call it teeming, right?
Definitely not.
But it's not lifeless. There's still stuff there. Maybe some deep-rooted plants, insects, maybe a tiny mammal hanging on. It's incredibly sparse.
Right. There is life, just very little of it.
Exactly. The cosmic voids are basically the universe's version of that.
Yeah.
The ultimate sparse environment.
Okay, so let's really get into that sparseness, that scale, because I think you're right. You can't grasp how empty a void is until you understand how empty the average universe is already, which is pretty staggering in itself.
Yeah.
We need that baseline. So the observable universe, right? This immense volume, 90-something billion light years across. The material we have lays out this fantastic thought experiment. Imagine you could take absolutely everything in that whole volume. Every planet, star, galaxy, gas cloud, and crucially, all the dark matter, dark energy too.
All the stuff.
And just spread it out perfectly evenly, like cosmic butter across the entire universe.
Right. A uniform smear.
What density do you end up with?
And the result is, well, it's mind-boggling. Really defines the emptiness we're sitting in. You end up with an average density of roughly, get this, one single hydrogen atom per cubic meter.
One atom in a cubic meter. Just try to picture that. A cubic meter, that's a pretty big box, right? Like arms outstretched, wide, high, deep. And inside that entire volume, just one solitary, lonely hydrogen atom floating around. That's the average density of everything.
It's almost nothing.
It's practically nothing. We only think the universe is dense because, well, most of that matter is crammed into tiny spots, like Earth or the sun or our galaxy.
Exactly. Gravity pulls it together.
The air you're breathing right now, the chair you're sitting on, that's trillions upon trillions of times denser than that cosmic average. It's wild.
It is wild.
Yeah.
It's almost impossible to visualize that kind of vacuum. I mean, even if you took that cubic meter box and sucked all the air out, cooled it to absolute zero, it would still be way denser than the universe's average. The vastness is just...
Okay, so that's our baseline. One atom per cubic meter, on average. Now, here's where the voids come in and just blow that away, because they are way emptier than that already incredibly sparse average.
Right. This is where it gets really interesting. They are the emptiest of the empty.
So how much emptier?
Well, when scientists model these structures, a typical void, averaging its density across its whole span, edge to edge, comes out at only about 1/5, so 20% of that average universal density.
20%. Okay, at first that sounds maybe not that much less, but wait.
Exactly. But remember what the average was. It was already basically zero. One atom per cubic meter.
So 20% of almost nothing is even closer to nothing.
Precisely. If the average universe is one hydrogen atom per cubic meter, a void averages out to only 0.2 hydrogen atoms per cubic meter.
0.2. So less than one atom per cubic meter on average inside a void.
Yeah. To put it another way, think about that box again. Instead of needing 1 cubic meter to find, on average, one atom, inside a void, you'd need a volume 5 times bigger. 5 cubic meters, a huge space, just to find that single lonely hydrogen atom on average.
Wow. Okay. That really drives home the scale of the desolation, I guess.
It really does. It fundamentally changes how you think about emptiness. And importantly, that 20% figure, that's itself a bit misleading.
How so?
Because it's an average density for the entire void, including its edges, its boundaries.
Yeah, right. And the edges are presumably where they bump up against the denser parts of the universe?
Exactly. They border the filaments and walls of the cosmic web where there's more matter. So those boundary regions are naturally a bit denser, relatively speaking. They pull the average up.
So if you could somehow just measure the very center, the deep interior?
It would be much, much lower than 20% of the average density. Way sparser. The vast majority of a void's volume is far emptier than even that 0.2 atoms per cubic meter suggests.
Okay. So they're these super vacuums, basically. But like you said, not totally zero. So what is that remaining trace amount of stuff? What contributes to that tiny bit of density? Let's move beyond just the numbers. What can we actually see or detect in there?
Right, what are the contents?
Yeah. Our deep galaxy surveys, the ones looking for the faintest light over huge distances, they do find things. It's sparse, very sparse, but it's specific stuff. We see things like dim dwarf galaxies, these little, often kind of raggedy-looking clumps of stars, galaxies that just didn't have enough material nearby to grow big and grand like the Milky Way.
The runts of the galactic litter, basically.
Pretty much.
Yeah.
And we also detect these incredibly thin, tenuous threads of gas, mostly hydrogen, sometimes linking these dwarf galaxies.
Whispers of matter.
Yeah, exactly. These are structures that are unbelievably hard to spot. They're so dim, they push our telescopes right to the limit. But they are there. It confirms the voids aren't perfect holes. They have some sparse furniture, maybe? Mostly near the edges.
That's the visible stuff, yeah. The baryonic matter, as we call it. The normal matter, like the dust motes you might see floating in a sunbeam in an otherwise empty room.
Okay.
But the picture gets way more complex and honestly more fascinating when we factor in the invisible stuff. Dark matter.
Ah, right. The mysterious scaffolding of the universe. We can't see it, but it's what, like 85% of the matter out there?
Something like that, yeah. Its gravity dictates where everything else goes. And even though we can't observe it directly, we can model its behavior with incredible precision using supercomputers.
Okay, so what do those simulations show happening inside the voids? Is the dark matter just not there?
Not at all.
Oh.
This is what's so cool. The simulations show that the voids aren't just smooth, empty holes in the dark matter distribution either.
Yeah.
They actually contain entire mini-cosmic webs made of dark matter.
Mini webs inside the voids, like
Yeah.
a ghost structure within the emptiness.
Exactly. A ghostly hidden scaffolding. Think of the main cosmic web, the big one, like this massive 3D sponge structure, or a network of connected filaments and walls.
Okay, yeah.
The voids are the huge holes in that sponge. But the simulations show that even within those giant holes, dark matter is still there, just at incredibly low densities. And its gravity, even though it's super weak, is still enough to pull it into finer, sparser structures.
So it's like webs within webs.
Pretty much. The source material we reviewed actually knows this complexity. It describes how voids seem to be divided into smaller subvoids. And those subvoids might be further divided into sub-subvoids, all defined by these incredibly faint filaments of dark matter.
Wow.
And this structure, this pattern, repeating at smaller scales, even in the emptiest regions, gives it what the researchers call a slight fractal character.
Fractal, like those repeating patterns in mathematics.
Sort of, yeah. It means the basic pattern of the cosmic web filaments connecting denser nodes surrounding emptier regions seems to repeat itself, even down here at these incredibly low densities within the voids themselves. It's a remarkable hint about how fundamental that web structure is to the universe's architecture.
Why is that significant, though? Does it tell us something important, that there's this faint fractal structure even in the voids?
I think it does. It shows that gravity, dominated by dark matter, is always at work, shaping things, even where there's almost nothing to shape.
Right, it's not just chaos in there.
No. That fractal character suggests that even the weakest gravitational fields operating over cosmic time still impose order and structure. It prevents even the voids from becoming perfectly uniform. It shows structure formation is still happening, just incredibly slowly and on a tiny scale compared to the main web. It tells us the void isn't just a hole, it's an integral structured part of the cosmic landscape.
So the big cosmic web has these holes, the voids, but the holes themselves have this faint ghost scaffolding inside, making even smaller holes within them.
That's a good way to picture it. And we have to keep coming back to those boundaries, those edges we talked about.
Right, the reason the average density isn't even lower.
Exactly. That 20% average figure relies heavily on the material clinging near the void's perimeter. The voids don't just stop. They, as the source puts it, butt up against walls and clusters and filaments of the main, denser cosmic web.
It's like the shallow edge of a deep lake, right? The edges make the average depth seem less than it is in the middle.
Perfect analogy. Those boundary regions are, by definition, less void-like. They have more dwarf galaxies, more gas, more dark matter influence from the nearby structures.
So they disproportionately bump up that overall average density figure, masking just how profoundly empty the real core of the void is.
Which brings us to the next step.
Yeah.
If we really want to talk about true, unadulterated emptiness, cosmic scale loneliness, we have to mentally zoom past those edges, past the dim little galaxies, past those faint gas threads. We need to go deep into the interior.
Okay.
We need to focus on the deepest, most isolated regions of the void's heartland.
This is where it gets really extreme, isn't it?
This is it. These areas, millions of light years away from any significant structure, any major gravitational pull. This is where the sources talk about the truly lifeless portions existing.
Lifeless in terms of lacking structure, lacking anything.
Pretty much. The information uses some really evocative comparisons to places on Earth, trying to give us a sense of the desolation.
Yeah, I saw those. Places like the Qattara Depression in the Sahara, or the Empty Quarter Desert, or Badwater Basin in Death Valley. Places known for being about as barren and dry as Earth gets.
Right, trying to anchor this cosmic emptiness to something terrestrial.
But honestly, even those analogies feel like they fall short. Massively short.
Oh, they absolutely do. Because when we talk about these core void regions, we're not talking about a few hundred kilometers of desert. We're talking about volumes of space where there's essentially nothing for distances up to millions of light years.
Millions of light years. Not meters, not kilometers. Light years. An almost unbroken vacuum stretching further than many galaxies are wide.
It just resets your whole perspective on empty. Traveling from one random particle, maybe a stray hydrogen atom, maybe a dark matter particle that happens to be zipping through to the next particle. That journey could take longer than it takes light to cross entire galaxy clusters.
Millions of years for light to cross the gap between stray particles.
Potentially, yeah, in those deepest cores.
So, if the density is effectively zero over such huge scales, why even call it a void with structure? Why isn't it just incredibly empty space? Is there anything physically stopping it from being a perfect absolute vacuum?
That's a really good question. Why isn't it just nothing? The reason it's classified as a void is structural, right? It's defined by its location between the denser filaments of the cosmic web.
Yeah.
It's the space carved out by gravity, pulling matter away from it.
Okay, so its existence is defined by what's around it.
Largely, yes. And physically, is it a perfect vacuum? No. Because quantum fluctuations can still, in principle, create particle-antiparticle pairs, though they annihilate quickly. And just random chance dictates that some particles will eventually pass through any given volume, even if incredibly infrequently.
So not technically 100.00% empty, but practically.
Practically, it's the closest thing imaginable. And crucially, the dark matter simulations back this up. They show this profound level of emptiness right in the cores of the voids. The random particle presence is so incredibly low, the source material really emphasizes this, that if you were sitting in one spot waiting for, say, a hydrogen atom or a dark matter particle to pass by, you would have to wait a really, really long time before the next one.
Really, really long time. Measured in cosmic timescales, probably.
Oh, easily. It's a vacuum so profound that meaningful particle interactions or collisions just don't happen. It's stillness on an unimaginable scale.
Okay, this sheer depth of emptiness, this near-total vacuum in the void core, it sets up this incredible thought experiment, one that really stood out in the research we looked at. It almost bridges physics and, well, philosophy.
It really does. It forces you to think about the link between the physical structure of the universe where we happen to be located and what that means for life, for knowledge, for civilization itself.
Right. So let's unpack it. The scenario posed is, what if? What if our solar system, the sun, Earth, all the planets, wasn't where it is now, inside a galaxy, inside a filament of the cosmic web? What if, somehow, it was transported deep into the core of one of these massive voids, millions of light years from anything?
Right, plunked down in the middle of that profound emptiness.
What would that even look like? What would the consequences be?
Well, the immediate visual impact, according to the analysis, is just chilling. And it dictates everything else, from Earth looking up at the night sky there would be no stars.
No stars at all.
None. Absolutely zero. The only things you'd see in the sky would be the sun, during the day obviously, our moon, and the other planets in our own solar system.
That's it.
Everything else would be projected against a backdrop of perfect, unending, unbroken blackness.
Wow. Just imagine that, looking up at night and seeing nothing but pitch black. Maybe Mars or Jupiter as a point of light, but absolutely nothing else. Forever.
We totally take the starry night sky for granted, don't we? It's the constant wallpaper of our existence.
Completely.
Yeah.
But we only see those stars. We only know we're in a galaxy because we happen to live in a relatively dense neighborhood. A brightly lit street, cosmically speaking.
Exactly. Being in a void changes everything for discovery. If you're that civilization on void Earth, the nearest external galaxy isn't just far away, it's millions of light years away.
And without any nearby stars or galaxies, how would you even know it was out there? How would you even begin to look?
That's the challenge. Even if this hypothetical void civilization developed telescopes just as powerful as ours today, say they built their own version of the James Webb Space Telescope,
Okay.
that nearest galaxy, millions of light years distant, would appear as just. The source describes it as a faint, dim smudge in the extreme distance.
It's a smudge. Not even a point of light, just a barely detectable fuzzy patch.
Barely detectable. Fainter than the faintest star we can see with the naked eye. It would require immense effort, long exposures, complex filtering, just to confirm it's even there.
So, this leads to a really profound, almost unsettling question, doesn't it? If you're that civilization, you look up, you see blackness on your local planets, would you ever even develop astronomy beyond just mapping your own solar system?
Would the motivation be there?
Right. Would you pour resources into building incredibly advanced telescopes just to hunt for a single incredibly faint smudge millions of light years away? Especially when there's no guarantee you'll find anything at all.
Think about the development of astronomy here on Earth. It was driven by observing the patterns of nearby bright objects, stars, planets, the Milky Way arching across the sky. That gave us data, questions, the drive to build better instruments.
But in the void.
In the void, astronomical observation beyond your own system would be incredibly tedious, expensive, and give almost no immediate payoff. The incentive to become cosmologists, to study the universe beyond your own backyard, it would be incredibly low.
The implications are just huge. If you don't see other galaxies easily,
You have no visible evidence for them.
you wouldn't see the large-scale structure, the cosmic web, because the walls are too far away. You wouldn't have easily measurable markers for things like redshift, which is how we figured out distances and the expansion of the universe.
Exactly. Measuring redshift relies on having lots of galaxies at different distances to compare. If your nearest neighbor is millions of light years off and looks like a smudge, good luck building a Hubble diagram.
So, they might never discover the expanding universe.
Very likely not.
They might never conceive of the Big Bang.
How could they? The evidence would be almost completely hidden from them.
Their entire understanding of physics, of reality, might be limited to just their own star system, floating alone in an eternal, unchanging darkness.
Which leads to that ultimate, chilling question the source material poses. Would they even know that the rest of the universe is out there?
Would they even suspect it? Or would they conclude that their solar system is the entire universe?
It's a profound thought. It really makes you realize how much of our own scientific understanding, our cosmology, our physics, isn't just a result of human ingenuity. It's also heavily dependent on our location, our lucky vantage point.
We're lucky to live in a busy neighborhood.
We really are. We're lucky to be bathed in the light from nearby stars and galaxies, lucky to be close enough to the large-scale structure that we can actually map it out. Our ability to measure things like redshift and the Hubble flow is only easy because we have thousands, millions of galaxies relatively close by to study.
If those data points were all millions of light years away.
The task of discovering cosmology would be almost insurmountably difficult, maybe impossible.
It really puts things in perspective. So let's just quickly recap the journey we took today. We started by trying to grasp the average emptiness of the universe.
Which is already stunningly empty, about 1 hydrogen atom per cubic meter on average.
Then we plunged into the voids, finding their average density is even lower, around 20% of that, maybe 0.2 hydrogen atoms per cubic meter.
But realizing that number is skewed high by the denser edges of the voids.
Right. And from there, we went into the true deep core, the heart of the void,
where the emptiness becomes almost absolute. Essentially, zero density for millions of light years at a stretch, broken only by the rarest stray particle or the ghost structure of dark matter.
The main takeaway then is that voids aren't just holes. They're fundamental components of the universe's structure. They define the walls and filaments by their very absence.
Exactly. And while they aren't technically perfectly empty, they have those dwarf galaxies, the gas threads, the dark matter mini-webs. The level of sheer desolation in their cores is a type of vacuum that's genuinely hard for us living here in our dense galaxy to truly wrap our minds around.
Which loops us right back to that void civilization thought experiment. Because the sources we looked at end with a really provocative twist on that.
Yeah, turning the question back on ourselves.
If a civilization in a void might never know the rest of the universe exists because the evidence is too faint, too far, well, what might we be missing?
What crucial aspects of reality, what fundamental structures or forces might be hidden from us simply because of our particular location?
How much of what we think we know about the cosmos is just down to the good fortune of living inside a bright, busy galactic filament where certain things are easy to see?
Yeah, it's a humbling thought, isn't it? Are there other cosmic structures, maybe operating on even larger scales or involving physics we haven't conceived of, that are currently invisible to us because we don't have the right perspective, or the signals are too weak from our vantage point?
What undiscovered cosmic realities are hiding out there simply because we're not in the right place or looking in the right way to see them yet?
It really underscores why things like large-scale simulations are so vital. They help us model the parts of the universe we can't easily see, like the full extent of the dark matter web and the true structure within these voids.
Because we can only directly observe this relatively small, brightly lit fraction of everything from where we sit. The simulations help us map the architecture of the whole thing, both the crowded places and the vast, profound absences. And understanding that absence, the void, is just as critical as understanding the galaxies themselves. It's all part of the same incredible cosmic structure, a structure we're still just beginning to comprehend.